the moments here, the Cm, we are talking about Cg, and the Cm variation with the angle of attack should be negative for a statically stable system, and the Cm naught should be greater than 0, right. So, what should be the Cg location in order to have the Cm alpha 0 and Cm naught greater than 0, Cm alpha less than 0 and Cm naught greater than 0, right. So, let us look into that. So, what is the condition criteria for static stability? Static Cm alpha has to be less than 0, Cm naught should be greater than 0. So, let us say this is your UAV, you have a wing and tail, right. So, when we are talking about longitudinal static stability, so let us talk about longitudinal condition. Case, right. So, longitudinal case is the motion in this vertical plane, right. That means it can translate front and back, go up and down, right. I mean go up and down in the sense it can perform a loop in this blackboard in this plane, right. We have a plane of symmetry for this aircraft, right. So, if we take a plane, a vertical plane, so which is cutting this aircraft exactly at this center line, right. So, about this plane you have a symmetry, right. This plane of symmetry is known as, the motion along this plane of symmetry is the longitudinal motion. Okay. So, that means, so in this vertical plane it can do pitch up, pitch down, that means a rotation, go front and back, move up and down. So, these are the three motions in this longitudinal plane. So, this motion about plane of symmetry, it is a motion in plane of symmetry, right. How many motions? 3 degrees of freedom. So, 2 translation, 1 rotation. Okay. Now, let us assume I cut this aircraft at this plane of symmetry, and say the aircraft has a CG located at some location, at some point here with respect to the leading edge, right. This is your CG. Now, when you are talking about longitudinal stability, which means what are the forces in this longitudinal plane? One is the weight, other one is the lift from the wing and lift from the tail. And say you have a pitching moment about the aerodynamic center of the wing, right. And generally tail is a symmetric aerofoil. So, the purpose of this tail is to create a moment rather than generating the force, generating a greater force. So, it is like creating a moment by generating a smaller force about the CG. Now, let us assume this as fuselage reference line, FRL. Okay. So, in some cases you also encounter I of W, that is inclination of wing with respect to this fuselage reference line. What is your wing setting angle, I of W, right. say this is your V infinity, and say this particular angle is your, say if I define angle of attack with respect to fuselage reference line, this is your alpha with respect to FRL. So the total angle of attack at the wing will be I of W plus alpha. Okay. Now for this case, what we assume is this FRL and the wing chord are along the same line. Okay. So I'm representing this whole wing as by means of this aerofoil, which is a root chord aerofoil, right? This is your root chord. So the root chord, so this is your root chord. It's a straight line joining the leading edge and the trailing edge of this root chord. And the root chord and this fuselage reference line are aligned with each other, right? They both coincide. So whatever the angle of attack that you see here is with respect to alpha, right? So that IW you can incorporate at any time, right? So say this is your aerodynamic center of the wing. This is measured parallel to this fuselage reference line, XAC of wing. This is your aerodynamic center, right? This is your XAC of wing. Say this is your CG, location of your CG. So this is XCG with respect to this leading edge, right? So now let us not consider the tail. Let us see, this is a wing alone, right? It's a wing alone system. We need to know how it fly, right? So the wing alone can also fly. See what should be the CG condition, how to get this Cm alpha negative and Cm naught positive to make it statically stable. So when I say there is a flow, there is a lift acting perpendicular to V infinity, and there is a drag, right? And also about aerodynamic center, we have something called moment about aerodynamic center of the wing. Do you accept this? Now if I write moment about CG of the aircraft, see moment about CG, when I say it's for the entire aircraft, right? I'm not exclusively writing this. Otherwise you can say moment about A by C is the aircraft, where A by C represents aircraft or UAV. Okay. This equals to, so this is the moment about CG, right? So there is a moment about aerodynamic center of the wing, moment about AC of wing, right, as it is, plus, why plus? Because the lift, so I should take the component of this forces acting perpendicular to this fuselage reference line, right? So what is the perpendicular to this fuselage reference line? So this is your fuselage perpendicular to fuselage reference. So the component of L along this perpendicular and the D along this perpendicular, which is L cos alpha plus D sin alpha, right, into, this is a total force acting multiplied by the distance between this AC and CG, which is XCG minus XAC of the wing, right? So this is XCG minus XAC of the wing, right? This I can express in a non-dimensional form, Cm about CG of the aircraft, or CMCC, CG is equals to half rho V square S into CMAC of wing into C bar. Sorry, please make a correction. It's a C. I missed C bar here. Right. So half rho v square S into C bar into CMCG is equals to half rho v square S into CMAC into C bar, right? Plus half rho v square S into CL cos alpha plus CD sin alpha into XCG minus XCAC of wing, right? Now what is CMCG? CMCG is equals to CMAC of wing. So by the way, the moment, so the reference area for this moment is a wing area, wing planform area, and the dynamic pressure is a dynamic pressure faced by the wing here, right? The reference dynamic pressure, half rho v square S into CMCG. This is because we are talking about moment due to aerodynamic forces about CG is equals to moment coefficient about wing aerodynamic center plus CL cos alpha plus CD sin alpha into the distance x bar CG minus x bar AC of wing, where x bar is equals to x by C bar. We are talking stability about this equilibrium, right? So this alpha is small, we assume the alpha is small, or say initially it is trimmed. Now we write the moment equation about this change in alpha, which is delta alpha, right? So what is the change in the force? How this change in the force is doing, right? Is going to affect the stability of the system. See, we talk about perturbation, about some equilibrium, right? So let us say CL is the lift generated due to a perturbed delta alpha. Right? Initially the moment is 0, that's a equilibrium. Now say alpha is the perturbed alpha itself, whatever the alpha that you have. So assuming alpha is small, right, what you have is CL cos alpha is 1 when alpha is small, and sin alpha is alpha, CD into alpha is further small compared to CL. So you can neglect this particular term. So what you have is CMCG is equals to CMAC of wing plus CL into x bar CG minus CL of wing here, CL of wing, CD of wing. So I'm sorry, I forgot to mention this. This is CL of wing and CD of wing. Right. CL of wing and CD. So x bar CG minus x bar AC of wing. Right? So can I express this entire pitching moment of the aircraft as Cm naught of the aircraft, or Cm naught about CG and Cm alpha about CG into alpha? This is equals to Cm about aerodynamic center of wing plus what is this CL of wing? CL naught of wing plus CL alpha of wing into alpha of wing into x bar CG minus x bar AC of wing. So where the Cm naught of this aircraft is CMAC of wing plus CL naught of wing into x bar CG minus x bar AC of wing. By comparing the constant and coefficients here, right? Cm alpha of the aircraft is CL alpha of the wing into x bar CG minus x bar AC of wing. Am I correct? See, we ultimately need what is the Cm alpha and Cm naught of the aircraft. So we are trying to arrive at that condition. So for a static stable system, let us say if this wing alone has to be statically stable, so you can assume it's a big wing, right? You can assume it as a big wing, the same wing what we have here, right? And the CG for that. Understand this? You assume there is a wing on either side and the CG along this axis. The wing is coming out in this direction, right? Now what should be the CG location in order to have a stable flight, right? So this is a wing alone configuration, right? So this Cm naught depends upon the Cm AC of the wing plus CL naught of the wing into x bar CG minus x bar AC. If this has to be positive, but let us look at what is Cm AC of wing. If I take a symmetric wing, the bottom one is a cambered wing and the top one is a symmetric wing, right? It's a symmetric wing, you can see. So for a symmetric wing, the moment about aerodynamic center of wing is 0, right? For a cambered wing, it is negative. This is a cambered wing, you can see it's a cambered aerofoil, and this is a symmetric aerofoil. So this is negative. For this, the moment about this aerodynamic center is always a negative quantity. Here it is 0, right? So say if you have a symmetric wing, what you have is Cm about aerodynamic center of wing is 0, right? So in that case what happens? So this is your ST1 stability, right? And tail sizing will perform from there. This is your ST2, ST3 say, stability equation 3. This is your ST4. This is your stability equation 2. Or say this is your stability equation 2, ST2. Right, ST2, ST3, ST4. Right. From ST3 and ST4, what you have is Cm naught is equals to Cm AC is 0 for a symmetric wing. So CL of wing into CL naught of the wing, right, into x bar CG minus x bar AC of wing. But for a symmetric wing, CL naught is equals to 0, right? Lift coefficient at 0 angle of attack is also 0. There is no lift at 0 alpha. So Cm naught is 0 for a symmetric profile. So for aircraft C in our previous case, when we are talking about Cm versus alpha variation, we witnessed like Cm naught is 0. When that can happen? When you have a symmetric wing, right? But to trim it at a positive angle of attack, you need to produce a continuous negative elevator deflection that gives you a positive moment to trim at a positive angle. That's again, if you are trimming elevator at a particular deflection, if you are trimming the elevator, that means you are giving constant deflection, right? That means increasing the drag there, induced drag at the tail, right? So the overall drag is also increasing. That's a penalty that you need to pay if you are going for a symmetric airfoil. So Cm naught is 0. What is Cm alpha? CL alpha of wing into x bar CG minus x bar AC of wing. So this quantity is not 0 because this slope, lift curve slope is positive. So this particular quantity has to be 0. That means the aerodynamic center should be greater than the CG. When it can be greater than, that means the CG has to be ahead of this aerodynamic center. Then you will have Cm alpha negative. But again, you can't fly at positive angle of attack. For this wing, which is symmetric with a symmetric profile, so in one case I try to bring it to the aerodynamic center, CG to the aerodynamic center, right? So in that case, it is continuously dipping down, right. So when I make it bit ahead and gave certain angle of attack during the flight, right, that means I am throwing it horizontal but orienting it at a particular angle, then it will glide to certain extent. After that it will try to, yeah, because as the angle of attack changes, you have negative moment here. With the increase in angle of attack, you have negative. Understand? So for an acrobatic aircraft, you need to produce equal force on either sides. So what is, so let us say if you performed a roll, right, so this, the aerofoil in this orientation should also produce equal lift, I mean lift equal to the weight. That means, so if you, for an acrobatic aircraft or a 3D aircraft, you need to use a symmetric aerofoil here, symmetric profile that produces equal force on either side. So if the AC is ahead of the CG, you have Cm alpha negative, right. For a wing alone configuration, to be stable, the aerodynamic center should be ahead of the CG. So in the other case where the Cm, so in the cambered aerofoil case, where the Cm about aerodynamic center is negative, if your symmetric cambered wing, Cm naught is equals to Cmac of wing plus Cl naught into x of wing into x bar Cg minus x bar AC, right, and Cm alpha is equals to minus, sorry, Cl naught of wing, Cl alpha of wing into multiplied by AC of wing. So for a cambered wing, if for Cm alpha to be negative, I need to have, since it is a wing alone configuration, irrespective whether it is a cambered or not, I need to have aerodynamic center ahead of the CG ahead of the aerodynamic center to make it negative. So this particular quantity is negative. Cl naught is positive for a cambered aerofoil. So this particular quantity is negative, and Cmac of wing is negative for a symmetric aerofoil. So Cmac is negative for cambered aerofoil, positively cambered aerofoil. So this Cm naught is becoming negative, that means you will not be able to trim at positive angles of attack. So for a wing alone UAV, in the introductory lecture we witnessed the flight test of a wing alone UAV, right. So for that UAV, if you want to design such a UAV, you need to use a reflex aerofoil, and this static margin or the, so in this case, like the distance between CG and AC, you should choose such a way that the Cm naught will be positive, is a marginally stable, marginally ahead, and this quantity should be higher than the product of this quantity. Okay. So otherwise you have to hold elevator up continuously. Got it, right? So for a wing alone configuration, to make it stable, you need to use a reflex aerofoil where the Cmac is positive in that case. So one such reflex aerofoil is NACA 23112. You can note it down. So NACA 23112, NACA 23112 for reflex, for positive Cmac, right, for positive Cmac. Now let's add a tail to it, right. See, it's a symmetric aerofoil, right. This is your chord of the tail. So this angle is known as tail setting angle I of t. The angle made by this chord of the tail with respect to fuselage refluence line is known as tail setting. Now again, this is your V infinity here. This is your V infinity free stream velocity. But we also studied about this. This is a wing, three-dimensional wing. You have a downwash and upwash effect, right? So induced downwash, you will have what is an induced downwash here at the tail because of the presence of the wing. Okay. So because of which there is a downwash at the tail that reduces the angle of attack. What is downwash? This is the downwash, that is a downward flow. So the resultant vector will be So this will be the resultant vector v. So v infinity prime is the actual velocity here. So the resultant vector at velocity vector at this tail is, so v infinity is the actual flight velocity and v infinity prime is the resultant velocity at the tail because of its downwash. Yes, sir. So the angle induced by this downwash is epsilon. Right. So this now it become bit flatter. Right. The v infinity prime will make a lesser angle compared to v infinity. These two are parallel and this angle is epsilon. So ideally this is your alpha t, right? With respect to v infinity and fuselage reference line, this is your alpha. Say this is your v infinity, right? This is your alpha. This angle is your alpha. Right. Now what is the angle of attack for the tail? This is your total angle of attack for the tail. Angle of attack is a angle made by the chord of the tail with respect to the free stream velocity, resultant free stream velocity here, that is v infinity prime. This is your alpha t, right? So what is alpha t? See, this I of t plus this angle is an angle, there is a resultant angle here which is alpha minus epsilon. This is alpha minus epsilon. Okay. So alpha at the t is alpha minus epsilon plus I of t. So this is a alpha at the wing. Okay. Where epsilon you can express this as the downwash, dou epsilon by dou alpha into alpha. This we already discussed. So during this discussion we will neglect epsilon naught will be, which is very, very small, right? And we know how to get dou epsilon by dou alpha from thin aerofoil theory, we discussed in our previous lectures. Now what will be the, so the angle of attack, effective angle of attack with respect to fuselage reference line is reduced here, right? So ideally this will be your lift that is generated at the tail, say, which is perpendicular to this yellow line. This is your free stream at the tail, this is your lift at the tail, and say if you consider the magnitude, it will be less than the wing, right? And you have drag at the tail, right? Now let us look at the moment equation about CG. Or say what is the total lift of this aircraft? Lift of the aircraft is equals to lift of wing plus lift of tail, right? Simple, right? There are two forces, upward forces acting here. There is a lift from the wing and the lift from the tail, the summation of both, or principle of superposition here. So this is half rho v square s into CL of aircraft is equals to half rho v square s into CL of wing plus half rho v infinity prime square s of t, because tail area is different compared to wing area, s of t into CL of tail. Okay. So if I express the non-dimensional lift coefficient of the entire aircraft is equals to CL of wing plus half rho, or say eta st by s into CL of tail, where eta is equals to half rho v infinity prime square divided by half rho v infinity square. It is a tail efficiency factor. So CL of the aircraft can be expressed as CL naught of the aircraft plus CL alpha into alpha of the entire aircraft, right, which is equal to CL of wing can be expressed CL naught of wing plus CL alpha of wing into alpha of wing plus eta ST by S into CL alpha of tail into alpha of tail, because CL naught of tail is 0 because we are using a symmetric tail here. So CL naught of wing plus CL alpha of wing into alpha of wing plus eta. You consider this as your stability equation 5. So this is your stability equation 6. So this is your stability equation 7. CL of aircraft is equals to eta into ST by S into CL alpha of tail. What is alpha of tail? I of t plus alpha minus epsilon. This I can express it as I of t plus, so with the help of this, okay, CL naught of wing plus eta ST by S into CL alpha of tail, right, into I of t plus CL alpha of wing plus eta ST by S into CL alpha of tail into 1 minus dou epsilon by dou alpha into alpha, 1 minus dou epsilon by dou alpha into alpha, eta ST by S into CL alpha of tail 1 minus dou epsilon by alpha into alpha, where I am taking alpha common. So substituting what is epsilon here by assuming epsilon naught as 0 here, let's substitute what is epsilon, you take alpha common from that, what you are going to get is, and separating the constant and the coefficients of alpha, right. So this is CL of the entire aircraft. So consider this as stability equation 8, right. Okay. Now comparing ST7 and ST8, what you have is CL naught of the entire aircraft is equals to CL naught of wing plus eta ST by S into CL alpha of tail into I of t, right, and CL alpha of the entire aircraft is equals to CL alpha of wing plus eta ST by S into CL alpha of tail into 1 minus dou epsilon by dou alpha. These are two equations, ST9 and ST10, stability 9 and 10. Now let us look at moment about CG. Because of the addition of tail, how the pitching moment is changing. So moment about CG for this wing and tail combination is, again even in this case what we do is, see further the angle is very small here. So we need to resolve this LT perpendicular to this V infinity, right. I mean while taking the moments we need to resolve perpendicular to this fuselage reference line, okay. And this particular distance, this particular aerodynamic center distance measured parallel to this fuselage reference line is x AC of tail. So this is your aerodynamic center of tail. This corresponding distance is x AC of tail here. Okay, I forgot to mention it. Please make a note of it. Now, moment about CG is moment about aerodynamic center of wing. So let us consider only the lift components, and cos alpha In either case, the change in the alpha is small. So let us consider only the lift directly. So that is how the end result will also have the same components, like the cos alpha will be considered as 1 and lift will be the corresponding contributor for pitching moment in this case. So Cm about AC minus L of wing, sorry, plus L of wing into XAC of wing, XCG minus XAC of wing minus L of T into XAC of tail minus XCG. Am I correct? Why? Because about CG, this lift of tail is giving you a negative moment. So L of T cos alpha, cos of epsilon minus alpha or alpha minus epsilon, which is considering it is a small quantity. So it will be L of T cos alpha, and D CD into this epsilon minus alpha minus epsilon is further small. So we neglected the other term here, drag contribution. So L of wing into XCG minus XAC minus L of T into XAC minus XAC of tail minus XAC here. So if you non-dimensionalize this is Cm about Cg is equals to Cm about AC of wing plus CL of wing into x bar Cg minus x bar AC of wing minus. So this you consider this equation as ST11 or 10? ST11. So consider this as ST11, this equation, stability 11, right? This is like eta ST by S into CL of tail x bar AC of tail minus x bar CG. So this ST by S into XAC of T. So generally L of T, length of tail, is considered as the distance between aerodynamic center of tail minus XCG, right? XCG. So the tail volume ratio is now defined as ST by S into L of T by C bar, right? This is considered as tail volume ratio. Please make a note of it, right? But I am not going to use this LT or VH here in this case. So we will see why we are not going to use. CmCg is equals to CmAC of wing plus CL of wing, which is CL naught of wing plus CL alpha into alpha of wing multiplied by the moment arm, corresponding moment arm, which is XCG, x bar CG minus x bar AC minus eta, because lift from the tail is contribute towards negative pitching moment, eta ST by S into CL alpha of tail into x bar AC of tail minus x bar CG into the alpha into multiplied by alpha of tail, right? This implies Cm about Cg is equals to Cm about AC of wing plus CL naught of wing plus CL alpha into alpha of wing into x bar CG minus x bar AC of wing, right, minus eta ST by S into CL alpha of tail into x bar AC of tail minus x bar CG into alpha of tail is 1 minus dou epsilon by dou alpha into alpha plus I of t. So consider this as this equation as stability. So So we know the pitching moment coefficient about Cg is equals to Cm naught about Cg plus Cm alpha into alpha, right, of the entire aircraft. This is Cg is about for the entire aircraft, right. So now comparing these two equations, what we have is Cm naught of the aircraft is Cm AC of wing plus CL naught of wing into x bar Cg minus x bar AC of wing, right, minus eta St by S CL alpha of tail into x bar AC of tail minus x bar Cg into I of t. Right. Similarly, Cm alpha of the aircraft is equals to CL alpha of the wing into x bar Cg minus x bar AC of wing minus the tail contribution eta St by S CL alpha of tail into x bar Cg minus x bar AC of tail minus x bar Cg multiplied by 1 minus dou epsilon by the alpha. So these are the stability equations, static stability equations for wing and tail combination. So consider them as ST13 and 14. This is stability 13 and this is stability 14. Now let us look at these equations. The Cm about aerodynamic center of the wing is negative, right? CL naught is positive, and in this case if the Cg is behind the AC, this is positive. So this contributes towards a positive term, a bigger positive term in fact, because Cm AC is far weaker than this, right? And eta minus eta St by S into CL alpha of tail, if the aerodynamics, so this is also a positive quantity, these are all positive St by S. So the only thing is negative here is I of t. If you have I of t negative, it becomes positive. So this becomes positive term. Cm. If I of t is 0, let us say, so you should have this Cm naught from the wing alone, Cm naught, required Cm naught. That y intercept in that curve Cm versus alpha need to be produced from the positive y intercept only from this term, these two terms. This is negative, right, for a cambered aerofoil. You need to design your the distance between, you need to locate your CG of the aircraft or the UAV in such a way that this particular term is positive enough, right, big enough to overcome this negative quantity. If I of t is 0, at 0 tail setting angle. What happens in this case? Cm alpha, say if the CG is behind the aerodynamic center, this is positive, CL alpha of wing is positive, so this particular term is positive. So I need to have enough distance x AC of tail minus x CG and the corresponding tail volume ratio here, right, which is multiplied by St by S, right. If this momentum multiplied by non-dimensional momentum multiplied by St by S is the tail volume ratio, so you should have enough tail volume ratio to give a Cm alpha negative. So the typical values of this tail efficiency factor is around 0.9, 0.95, right. So you need to locate your CG to make this condition satisfied. So we have the conditions for stable and unstable, right. So do you have something called in between these two, a limiting condition for this? We have something called neutrally stable system. For example, if I take this tape, it's a two-sided tape, right. So if I take this roll and start throwing it on this table, right. So this is one equilibrium, let us say now it is at rest. Now if I apply small force, okay, it has gone down, okay, it has become. So what happens is, if I apply small force, it will go and stop at a different location. So, this is a tape, if I roll it down, so yes, it reached a different equilibrium point, right. So, it altogether attained a new equilibrium point, right. So, it is neither unstable nor the stable, it has achieved a new equilibrium point. We can't comment about stability about this particular point. So, this is a limiting condition for this stability, stable and unstable system called neutral stable system, where if you just apply, see this is also a stable case here, if I apply a force it is attaining a new equilibrium here, right. So, this particular condition is known as neutrally stable condition.